We're now ready to bring out the big guns in image classification and machine learning, so-called neural networks. At the core of a neural network are neurons, which sounds really complicated and something much more sophisticated than what we've been doing before, but it's not really. At its core, the neural network is doing something very similar to what we've seen from least squares, total least squares, linear discriminant analysis, and linear SVMs. They start with linear models. Okay? Now, the main difference that you'll see when you see neural networks is that they are rendered a little bit differently. So where we're going to start is where we've been, linear models. I'm trying to predict some class Y from a linear combination of inputs. W are my weights, X sub I is my data, and now here I'm in an n-dimensional space, and here is my constant offset. This we have been doing for over and over and over again and forms the basis of a neural network, a neuron in particular. We just tend to draw these things a little bit differently, so let me show you how we're going to draw it. Let me first say that my renderings of neurons and neural networks are going to be a little bit different than the standard ones you see in the literature because I don't like the way networks are typically represented because they often muddy the water between what is data and what is computation. And I think early on particularly it's important to understand where the various parts are. So this may look a little bit different, but I'm hoping that you'll understand it clearly. So we have a bunch of inputs, x1, x2, xn. That is the input into your system. If we are fitting a line to XY data, this would be x1, x2. Okay. We have weights of the linear model, W1, W2 to Wn, each of which is multiplying the corresponding dimension in the input. So so the weight comes in, the data comes in, and we do a multiplication in this green circle here. We take the result of all of those multiplications and we sum them, and this of course is what is considered to be the neuron because it's taking a bunch of inputs and then outputting something. Notice, by the way, that the output here is just a linear combination. In fact, it's a dot product between W and X. Nothing complicated, nothing new. We need to bring this B into here, by the way, because it's that constant that is part of our linear model. And so I'm going to drag it in over here. I don't like dragging this thing along that is sort of separate from here. So the way I'm going to render that is going to be a little bit different in a minute. Now, let's make sure we understand the various parts of this neuron. I've added in a new component, which I'll describe in a second. We have our input, x1 to xn. The data is in an n-dimensional space. We have an unknown set of weights in red. Those are W1 to Wn plus the offset B. And that's what I have to learn, the same way I've learned that through least squares, total least squares, logistic regression, or whatever. And then I've got my class output, my output of the neuron, which is here Y. And then we optionally can push that through a nonlinearity F to get the final output Y hat. We've certainly seen all of this before, linear models. Nothing complicated, I'm just rendering it differently. We've also seen this, the sigmoid and logistic regression. So if I put a sigmoid here, I've got a linear model, inner product, summation, sigmoidal nonlinearity, output. Okay, so this is the building blocks of a neural network. Of course, this is only one small part of a larger network. We'll talk about the larger networks in a little bit. So again, Y is the output of a linear model. Y hat is the output of a nonlinearity applied to that. Why nonlinearities? Well, we saw one nonlinearity, the sigmoid, and the benefit of that when we were doing logistic regression because it caps the output between 0 and 1. And we'll see other nonlinearities and what their benefits are when you plug them into these linear models. As I said, I don't like lugging that B around separately, so I'm going to add in a W0 and then just tack a 1 on into the input. And we've seen this before where we don't want to, we have our linear model here plus the constant term. Well, if we just assume that x0 is 1, as I've done here, then W0 will be the offset B term, which I'll now call W0. And so in this way, I have all my outputs here, my learned things, my model here, and then the computations to get to the output. And of course, this is still supervised learning. And so the way we're going to learn these weights is we have a bunch of inputs that are known, a bunch of outputs that are known, and we are going to use the weights to learn them. as we have seen with everything from least squares to logistic regression to SVMs, linear and nonlinear. Okay, now, what goes here? This turns out, by the way, nothing new here, right, on this linear part. We've been doing this. So really, the magic of neural networks, if we can call them magic, is really what we do here and then how we combine these into larger and larger networks. This is, of course, just one neuron here or one set of computations. So what are your options here? Well, it could just be linear. I could just say, look, I've got a linear model, and I'm not going to do anything to it. And so the output is y hat is just y in this case. We have other options. We can do a sigmoid. We've already seen that. That was what we did for logistic regression, in which case now y hat is 1 plus 1 plus e to the minus y. That's the sigmoidal nonlinearity we saw with logistic regression and with contrast enhancement much, much earlier in the semester. We have other options. We can do a so-called binary nonlinearity. I hinted at that earlier on, where y hat is 1 if y is greater than or equal to 0, and 0 otherwise. So now look what I have. Instead of the slow change from 0 to 1, I have an abrupt change. Is that good? Is that bad? We'll see what happens later on. This is so-called a binary or a perceptron is what it is called when the nonlinearity has this hard edge here. You have other options. You have a so-called rectified linear unit, ReLU, which looks something like this. Y hat is y when y is greater than or equal to 0, and 0 otherwise, when it's less, sometimes also called half-wave rectification, where the positive values, you keep their value, and everything that is negative is 0. That's another form of nonlinearity that you will find in a network. When do you use it? Why do you use it? That's time for there's a time for that conversation later. You can also write that nonlinearity as just as taking the max of 0 and y. You'll see it in both ways. So the building blocks of an artificial neural network, deep networks, convolutional networks, all the things that are the rage in computer vision today are really nothing more complicated than really everything we've seen before. And there's a reason for that, by the way. Those are really powerful models. And then how we start to put them together is going to be part of the power of neural networks.